Imagine you are exactly 3 minutes away from the surface of the moon.
Oh man, talk about pressure.
Right. You are strapped into this tiny, violently vibrating metal box, and you're just hurtling through a vacuum at thousands of miles an hour.
With the whole world listening.
Exactly. Humanity's absolute greatest achievement is resting squarely on your shoulders. And then suddenly, your spacecraft's computer just starts throwing alarms.
Yeah, alarms you have literally never seen before.
Blaring, numerical warnings lighting up the console. So, what do?
I mean, it is the ultimate nightmare scenario for a system. You are completely dependent on this machine to calculate your descent, and the machine is essentially throwing its hands up saying, I'm overwhelmed.
Yeah, and the natural human instinct right there is absolute panic. You either abort or you crash.
Right, but the computer didn't freeze up completely.
No, it didn't. And the only reason Apollo 11 didn't end in a catastrophic abort or, a fatal crater on the lunar surface comes down to the brilliant, incredibly stubborn foresight of one person.
Margaret Hamilton.
Yes. We are taking a deep dive today into a really comprehensive set of sources, anchored by an extensive Wikipedia article, all detailing the life and work of Margaret Hamilton.
It is such a remarkable narrative to dissect. I mean, we are looking at how her highly rigorous, almost unorthodox approach to problem solving not only salvaged that mission, but basically established the foundational paradigms of software engineering.
Okay, let's unpack this, because to truly understand how she engineered a system capable of saving the moon landing, we have to look at how someone even enters a highly technical field that, well, it literally did not exist yet.
Right, there was no such thing as a software engineer.
Exactly. So Margaret Hamilton was born in 1936 in Indiana, and she ends up studying mathematics at Earlham College.
And she was heavily influenced by the head of the math department there, right? Florence Long.
Yeah, Florence Long really pushed her toward the rigors of abstract mathematics. But the interesting part is Hamilton also took on a minor in philosophy.
Which is huge. That combination is really the critical bedrock of her entire methodology.
Oh, for sure.
The sources mention she credited her father, who was a poet, and her grandfather, a school headmaster, for inspiring that deep philosophical curiosity.
So she wasn't just like crunching numbers.
Exactly. She was fascinated by the underlying architecture of thought itself.
So I want to run a premise by you based on that. When you look at coding, especially in its purest punch card era form, is it essentially just applied philosophy?
That is a really interesting way to put it.
Right, because you are taking strict logical rules, conditional statements, and a highly constrained language, and you're using them to dictate how a physical system has to behave in the real world.
I'd probably push back slightly on the word just, but the parallel is definitely strong. I mean, formal logic in philosophy is about setting up premises that guarantee an inescapable conclusion.
Right.
But when you apply that to a machine, you introduce the chaos of physical limitations.
Like hardware faults and memory constraints.
Exactly. Processing speed, all of that. So it is applied philosophy, but it's applied philosophy forced to survive in a hostile physical environment.
Which brings us to 1959, when Hamilton goes to work at MIT.
In the meteorology department, working for Edward Norton Lorentz.
Yeah, and again, there are no computer science degrees. She is programming on these massive, primitive machines, the LGP-30 and the PDP-1.
And she's building weather prediction software.
Which seems like a massive leap from abstract college math.
Well, weather is the ultimate test of chaotic systems. Her work there actually contributed to Lorentz's foundational publications on chaos theory.
Oh, wow. I didn't realize she was directly involved in that.
Yeah, she was taking the absolute unpredictability of the natural world and trying to force it into the strict, unforgiving binary logic of early computers. And she had to learn everything hands-on.
Because there's no operating system to hold her hand.
No compiler to catch her syntax errors, none of that. You were manipulating the state of the machine at the lowest possible level.
So she's basically squeezing chaos into a box.
Exactly.
And that experience transitions her directly into the SAGE project. From 1961 to 1963, she moves over to the MIT Lincoln Lab.
SAGE was a massive Cold War military installation.
Yeah, they were writing software for this giant prototype computer, the ANFS-Q7, designed to track potentially hostile aircraft on radar.
Which is incredibly high stakes.
And this is where she encounters a piece of early computing culture that sounds like a joke, but was actually a massive test.
Oh, the Greek and Latin code. It is such a fascinating look into the early hacker ethos of the 1960s.
The sources describe how, when a beginner joined the lab, they were handed this specific, incredibly convoluted program that nobody had ever been able to figure out or run.
Right, the original author was essentially a workplace troll.
Totally. They took delight in writing all of their code comments and all the system outputs entirely in Greek and Latin.
It was a deliberate adversarial obfuscation of logic. It wasn't just hard to read, it was designed to actively confuse anyone trying to follow the execution path.
And Margaret Hamilton is handed this nightmare program.
And what does she do?
She doesn't just trace the logic, she actually gets it to run. She was the very first person in the lab to do it. It even printed out its final calculations in Latin and Greek.
Which is hilarious, but the broader implication of that anecdote is what really matters here.
How so?
Well, she wasn't just learning the syntax of a specific instruction set. By untangling that deliberately obfuscated, messy human logic, she was training herself to map out complex state machines in her head.
Ah, I see.
She was taking her abstract math and her philosophical logic and applying it to reverse engineer a broken system.
Right.
That specific cognitive skill, being able to see through the noise to the underlying architecture of a system, is the exact prerequisite you need if you were going to design software that absolutely cannot afford to fail.
Here's where it gets really interesting, because all of that preparation, the weather chaos, the hardware constraints, and untangling Greek code, it all collides on July 20, 1969.
Apollo 11.
Yeah, she had joined the MIT Instrumentation Lab in 1965, becoming the first programmer hired for the Apollo project.
The first female on the project, too.
Yes. And eventually she becomes the director of the software engineering division. And 3 minutes before the lunar lander reaches the surface, her code is put to the ultimate test.
The famous 1202 and 1201 program alarms. The executive overflows.
Let's break down exactly what happened mechanically here, because the sources are highly specific about this. Buzz Aldrin had entered a code to request that the computer display rendezvous radar data.
Right, something he had practiced in the simulator.
Yeah, they keep track of the command module orbiting above them. But the Apollo guidance computer was designed to support a maximum of 7 simultaneous programs. Aldrin's radar request was the 8th.
That is part of it, yes, but the underlying hardware issue is what made it lethal.
Right, the incorrectly phased power.
Exactly. The lander's rendezvous radar was being supplied with incorrectly phased power. So essentially, you had 2 different power supplies interacting, and their alternating current signals were slightly out of sync.
Meaning, the computer was looking at the electrical signal from the radar, and because the wave was out of phase, the hardware interpreted that as a continuous stream of new data arriving.
Precisely. It generated a continuous flood of hardware interrupts.
And for people who don't know, an interrupt literally forces the CPU to stop whatever it's doing.
Yes, it stops, saves its current state, and addresses the new input. This radar glitch was stealing up to 15% of the computer's total processing cycles just to count meaningless radar noise.
Wow.
So when Aldrin asked for the display program on top of that, it pushed the CPU utilization past 100%. The system was drowning.
It's comparable to a modern computer experiencing an interrupt storm. Like you were trying to render a massive video file, and suddenly a faulty USB port starts sending 10,000 connection requests a second.
The CPU just spends all its time context switching instead of doing the actual work.
Exactly.
Yeah.
System completely locks up, the mouse won't move, and you suffer a kernel panic. Except here, if the Apollo computer kernel panics, the landing engines shut off, and the astronauts hit the moon at orbital velocity.
Which is why Hamilton's architecture was so incredible, it prevented a complete system lockup.
So how did she actually do that?
This is her masterstroke. Hamilton and her team had designed what was called asynchronous flight software.
Okay.
In a standard synchronous system of that era, the computer processes tasks in a rigid, fixed loop. Task A, then task B, then task C.
Right. And if task A gets stuck or takes too long, the whole loop freezes.
Exactly. Hamilton threw that paradigm out.
She implemented priority scheduling.
Yes. Her asynchronous system assigned a strict numerical priority to every single job.
Oh, that makes sense.
So when the hardware interrupt storm hit and the CPU realized it didn't have enough time to finish its cycle, it generated those 12-0 saddle alarms, the executive overflows.
But instead of crashing, the software was programmed to look at its memory queue, recognize the overload, and aggressively purge all low-priority tasks.
It actively dumped the radar data processing.
Just threw it out.
Yep. It looked at the queue and decided that maintaining the engine thrust vector and calculating the descent profile were the only things that mattered.
It was a built-in survival instinct for the machine.
Exactly. It dropped the dead weight and focused exclusively on the landing.
But she didn't just write the code and hope the computer handled it silently. She really understood the interface between the machine and the human.
The priority displays.
Yes, she had implemented a fail-safe, known as priority displays.
Hmm.
She knew that if these alarms popped up, interrupting the astronauts' normal data screens, there was a massive risk of the human pilots acting rashly and slipping out of sync with the computer state.
So she gave them an incredibly counterintuitive instruction.
Yeah, she instructed the astronauts that if a priority display pops up, they should literally count to 5 before hitting any buttons.
Just count to 5.
Right. In the middle of the most high-stakes, terrifying descent in human history.
Because you have to give the CPU a handful of clock cycles to catch its breath, clear out the suspended tasks, and switch over to the stripped-down survival programming.
What she created there is the ultimate man-in-the-loop architecture.
Absolutely.
The software didn't autonomously lock the pilots out, but it also didn't let them accidentally crash the queue. It presented a clear, prioritized state to the astronauts and to mission control.
And Jack Garman, the NASA computer engineer back in Houston, recognized that specific 1202 error code.
Yeah, he knew Hamilton's architecture.
Yeah.
He realized the computer was doing exactly what it was designed to do, shedding the load, and he made the call to go.
Hamilton referred to it as a system-wide kill and recompute from a safe place.
Kill and recompute. I love that.
It's brilliant. Recognizing an error state, safely terminating non-essential processes, and restarting the core loop from a known, mathematically proven baseline.
And that specific architecture is the absolute foundation of ultra-reliable software design today.
Without that asynchronous architecture, the Apollo 11 computer would have hard-faulted, and the mission would have aborted.
Which brings us to the broader implications of her work. Saving the moon landing was the definitive, undeniable proof that code, this invisible mathematical construct, is just as critical to the survival of a mission as the titanium bulkheads or the rocket fuel.
It was a profound paradigm shift. Up until Apollo, software was very much the neglected afterthought of the engineering world. It wasn't considered a rigorous discipline.
Yeah, the sources explicitly note that Hamilton actually coined the term software engineering during the Apollo era.
She began using it to distinguish her team's work from the hardware engineers, insisting that both domains required equal respect and rigorous systems-level analysis.
And she faced immense pushback for using that term.
Oh, a ton of pushback.
I want to examine that friction a bit. The Wikipedia article notes that her use of the term software engineering was considered an ongoing joke for a long time among her peers. They teased her about her radical ideas. Was that resistance primarily because software was invisible compared to hardware? I mean, you can measure the stress tolerance of an aluminum strut, but you can't weigh a line of code. Or was it because a woman was spearheading this charge to legitimize a new science in a massively male-dominated 1960s culture?
Honestly, it is highly likely a compound of both factors. The engineering culture of the 1960s was overwhelmingly hardware-centric.
Right, real engineering.
Yeah, in their worldview, real engineering involved thermodynamics, metallurgy, and physical tolerances. Software was often viewed as akin to clerical typing.
Just punching holes in cards to tell the real machines what to calculate.
Exactly. Elevating that to the level of an engineering discipline was radical enough. The fact that the person demanding this elevation was a young woman certainly challenged the entrenched demographic hierarchies of the Apollo program.
But Hamilton herself noted that the turning point wasn't a cultural debate, it was undeniable results. She recalled a memorable day when a highly respected hardware guru publicly agreed with her in a meeting.
He stated, on the record, that the process of building software should be considered an engineering discipline, just like hardware.
Because the math saved the mission. You cannot argue with a successful lunar landing when the hardware threw an anomaly that should have been fatal.
And she didn't stop at Apollo. She was deeply concerned with legitimizing software development, not just as a title, but as an actual mathematically provable science.
So in 1976, she co-founded a company called Higher Order Software.
Creating a product called USC.IT.
Right. Then in 1986, she founded Hamilton Technologies.
Those companies were the vehicles for her ultimate philosophy, something she called the Universal Systems Language, or USL.
The USL is fascinating because it is built entirely on her experiences with those Apollo hardware constraints. The core paradigm of USL is called development before the fact.
Let's break down how this actually works.
Okay. In modern software, the standard practice is to write the code, compile it, and then run massive suites of automated tests to find the bugs.
You are constantly patching leaks.
Yeah. Hamilton's philosophy was the exact inverse of that.
Testing for errors after they are written means you are searching through an infinite space of possible mistakes. It is inefficient, and in mission-critical systems, it is dangerous.
So USL uses mathematical modeling to prevent the bug from existing in the first place. I want to try an analogy here to see if I am grasping the mechanism.
Go for it.
It is less like building a house and hoping the roof doesn't leak during a storm, and more like writing a mathematical proof. If you define the state boundaries perfectly, using strict axioms, an undefined behavior, like a bug, literally cannot compile. The equation won't balance.
That is a much more accurate way to visualize it. It relies on a rigorous concept of state machines.
Okay.
In USL, you define the system entirely through preventative mathematical models. If the logic governing the transition from state A to state B is mathematically sound, then an unpredictable state C cannot physically execute.
She was bringing that strict philosophical logic she learned at Earlham College into a field that was rapidly degrading into a culture of trial and error.
She wanted perfection built into the language syntax itself, so the architecture inherently rejected flawed logic.
Which is a stark contrast to how we live today. We just accept broken apps, day one patches, and systemic crashes as a normal part of the digital experience.
Very true.
So what does this all mean? How does a deep dive into 1960s asynchronous spaceflight architecture matter to you, listening to this right now?
Beyond the historical awe, I think there is a profound masterclass here in managing cognitive overload.
You are looking at the priority display concept as an operational framework.
Exactly. Think about your own daily workflow as a computing system. When you are overwhelmed with tasks, your inbox is flooding, Slack is pinging, you have a hard deadline approaching.
The metaphorical power supply is incorrectly phased.
Yeah. Throwing constant interruptions at your brain, what do? Most of us try to process all the alarms simultaneously. We try to context switch fast enough to handle it all. And human cognition suffers from the exact same interrupt storms as that 1969 CPU. The context switching eats up all your processing power, leaving nothing for the actual task.
You executive overflow.
Right.
But Hamilton's asynchronous architecture provides the blueprint for survival. Build a failsafe. Recognize the error state. Deliberately drop the low-priority tasks immediately.
Kill the noise.
Yes. Take a breath, count to 5, and recompute your queue from a safe place. Focus entirely on the landing. Drop everything else to ensure the most critical mission objective survives.
It is deeply pragmatic advice. Treat your attention like core memory. It is finite, and it must be fiercely protected from low-priority interrupts.
The world did eventually recognize the sheer sweeping scale of her impact. The tributes she has received are staggering.
They really are.
In 2003, she was given the NASA Exceptional Space Act Award for her scientific and technical contributions. The sources point out that this award came with a $37,200 payout, which was the largest financial amount awarded to any individual in NASA's history up to that point.
A rare, tangible acknowledgement from an agency that historically favored hardware achievements.
Then, in 2017, she was immortalized in a Women of NASA Lego set.
Oh, I love that one.
It featured a minifigure of her standing next to a recreation of the famous 1969 photograph.
The one where she is standing next to a physical printed stack of her Apollo software code listings.
Yeah, and the stack of paper is literally as tall as she is.
It remains one of the most powerful visual representations of software ever captured. It makes the invisible math tangible.
In 2019, to celebrate the 50th anniversary of the Apollo 11 landing, Google utilized the massive arrays of mirrors at the Avampas solar power facility in the Mojave Desert.
They configured thousands of solar mirrors to project a massive illuminated portrait of Hamilton and the Apollo spacecraft using moonlight.
An incredibly fitting tribute, using physical geometry to reflect her legacy.
Definitely.
And of course, in November 2016, she received the Presidential Medal of Freedom from Barack Obama, the absolute highest civilian honor in the United States.
She didn't just write the code that landed humanity on the moon. She shattered the demographic expectations of her era and fundamentally established the rules of engagement between humanity and complex machines.
She defined the boundaries of control.
Absolutely.
Which leaves us with one final, slightly provocative thought to ponder as we wrap up this deep dive. Margaret Hamilton started her programming career at MIT, trying to predict the chaotic, wild, totally unpredictable nature of weather systems.
Right.
She then took the lessons of that chaos and used them to forge the flawless, strictly controlled, mathematically perfect logic needed to safely navigate the vacuum of space.
She moved the discipline from accepting chaos to demanding total control.
But look at the trajectory of our current technology. Our modern computing systems, especially with the exponential rise of complex machine learning models, neural networks, and generative AI.
They are becoming less like the strict logical calculators Hamilton built.
Exactly, and more like those unpredictable weather systems she started with. They are highly chaotic. They hallucinate data. They operate inside black boxes where the exact logic paths are opaque.
We are building architectures that generate outputs even their original creators cannot fully map or predict. It is a return to chaos.
So the real question is, as our own technological creations become increasingly chaotic and opaque, are we going to need an entirely new generation of Margaret Hamiltons?
That is a great question.
Will some future engineer have to invent an entirely new discipline of logic, a new development before the fact for the artificial intelligence age, just to keep our own creations from overflowing the system?
It is a sobering thought. We may need to relearn how to build a failsafe for systems that think faster than we do.
So, the next time you feel like you are 3 minutes from crashing into the surface of your own personal moon, overwhelmed by the alarms of daily life, remember the philosopher-mathematician who taught computers how to take a deep breath, dump the noise, and just stick the landing?